In this video, we're going to take a look at the hyperbolic functions. And so the first thing I want to do is just give you an idea of what these are. These are going to be different. We're going to think about trig in a slightly different way. So the trig functions that we have studied always measure sides along the unit circle, the ratio of sides along the unit circle. The trig functions measure the ratio of sides of the unit circle given angle theta. So unit circle on our xy plane, we're given a theta. Well, sine, cosine, tangent measure these sides right here. They measure the sides of the triangle formed by that unit circle. We know that x is equal to cosine theta, y is equal to sine theta. We can write tangent as sine over cosine because it's the y over the x, so forth. The hyperbolic function hyperbolic functions measure the distance from the origin to a point on the unit hyperbola. I'll put unit in parentheses. Kind of like we measured along the unit circle before, we're measuring it along the unit hyperbola now. So if we think about what a hyperbola looks like, this shape right here, where we're looking at a unit away, each thing is just counting up by a unit. So if we have our asymptotes there, they're units long. And so if we were to look at a point along that, this point would be the point, the hyperbolic cosine, or the cosh function, cosh theta, comma, sinh theta. And so we are dealing with somewhat of the same trig functions. We have the sine, the cosine, the tangent, cosecant, cotangent, and secant, but they're now the hyperbolic trig functions. So we have the what looks like a cosine with an h, and then a sine with an h read cosh and sinh. Or you might hear some variants on pronunciations here, but you'll hear me refer to them as the cosh and the sinh. So now the x-coordinate is given to us by the cosh function. The y is the sinh. Now that's already leading us to believe some of the ideas from trig are going to stay the same. So we'll look at those as we go through this section. To just give you some applications, because these are different, when would we use these sorts of things? Well, when we're measuring along the hyperbola. We've seen that there are a number of places that hyperbolas come into play. If we are looking for coordinates along that hyperbola, these are a great application of those. Examples of this could include, think about hanging cables. That cable hangs in a hyperbolic path, so if we want to know a point along that cable, that would be a good application. Electromagnetic theory a lot of times uses these hyperbolic functions, and so again, there it could play in. So heat transfer, fluid dynamics, things like that. Latitudes, longitudes, we have these hyperbolic paths along curves. Well, hyperbolic functions may be a good way to track things moving along those paths. Let's define what the sinh function actually is. The sinh function, sinh of x, is equal to e to the x minus e to the negative x over 2. And the cosh function of x is equal to e to the x plus e to the negative x over 2. And let's view these in terms of their graphs, because I think that helps. So remember, these are just the distances along the xy plane of the hyperbolic function here. So if we think about the sine as being the heights, well, if we think of an angle of 0, notice if we start at an angle of 0, the height is just 0. And so we have the point 0, 0 here. And then from there, what happens is as angles grow more and more, that then gets larger and larger at a much, much faster rate. And if we're to go below zero, or angles beneath zero, same idea, starts out a little bit of height, a little bit of height, then it's growing much, much more rapidly as we go along. And so it looks almost in a way kind of like the x cubed function. Again, it's not going to be the same values, completely different values. But where the e's are playing in here are there the limiting functions. They're how the curve is bending because of that hyperbolic structure. If we're to look at the cosh function, well, cosh, if we start out at 0, actually has an x value right away. It has an x value of 1 because, again, we're thinking of that unit hyperbola starting at 1. And then as we see those x values grow, the x values are going further and further away at a much faster rate. It's curving away much faster. As the theta values shrink, we see that x values are negative. And so we have what looks to be almost a not hyperbolic, but a parabola with the y-intercept at 1. Not parabolic because it is following this hyperbolic structure. It is following a hyperbola. So it's bending according to these e's here. These e's are giving it its structure. Just to real quickly sketch out what the others would look like. Well, if we think about tangent, or the hyperbolic tangent function, the tench function, we can think of that in terms of sine and cosine. It'd be the sinh over the cosh. And we know that sine, the sinh rather, is the e to the x minus e to the negative x over 2. Cosh is e to the x plus e to the negative x over 2. Notice we can divide those twos, and so we'd have e to the x minus e to the negative x over e to the x plus e to the x. Remember, negative x. I told you there's going to be a lot of similarities with trig, so we still have this idea of the ratio of sine and cosine giving us the tan function. And so to view its graph, we could see that the ratio of y's to x's would be 0, because when our sine was 0, when our angle was 0, sine was 0. And then from there, it's going to be moving out like so. And we could do, and there are asymptotes here, I should point out. There are asymptotes at 1 and -1 because the ratios of the sine and cosine are following those asymptotes on the graph. And so there has to be some limiting factor between the two of them. We could do this for all of the trig functions. The the hyperbolic cotangent function, or the coth, or you might hear coch from some people, but I say coth, would be the cosine over the sine. The cosh over the sinh. The sech function, or the hyperbolic secant, is simply 1 over the cosine hyperbolic function, or the 1 over the cosh. The cosinh function is 1 over the sinh. Cosech function, excuse me, is 1 over the sinh. And so we could express all of these in terms of those e functions as we had done initially. The coth is e to the x plus e to the negative x over e to the x minus e to the negative x, which another way to think of about that would be 1 over the tanch function. The sech function is simply 1 over the cosh, so that is equal to 2 over e to the x plus e to the negative x. And then the sinh, because it was the minus case, we'd have 2 over e to the x minus e to the negative x. So we're noticing a lot of the same identities, or a lot of the same properties for these hyperbolic functions as we saw for just the trig functions. Let's talk about some other identities. So some other identities for these hyperbolic functions. Cosh squared minus sinh squared is equal to 1. That looks kind of like which other one, I need an h in there, sinh, Kind of like what other one in the trig functions, looks a lot like the Pythagorean, but not quite, right? It's supposed to be a plus. Really, it looks more similar to our double angle because it does relate to the double angle formulas. And so if we think about our other double angle formulas, we would have sinh 2x is equal to 2 sinh cosinh, which is exactly the double angle formula. And then we can write cosinh of 2x is equal to not cosinh, but cosh. Cosinh, you can say it either way, really. Would be the same as cosh squared plus sinh squared, which is another of our double angle formulas. If we think of some of our other formulas that we've seen before, we have the power reducing. Cosh squared x is equal to cosh 2x plus 1 over 2. And sinh squared x is equal to cosh 2x minus 1 over 2. I'll keep going sideways for my other power reducings. Tan squared x is equal to 1 minus sech squared x. Not actually a power reducing, sorry, that is more similar to, those are Pythagoreans. And then coth squared x is equal to 1 plus cosinh squared x. So a lot of kind of holdovers from before. Let's do one proof. Let's take the proof of cosh squared x minus sinh squared x and see what see that's actually equal to 1. So if we think about this cosh function, remember the cosh function is e to the x plus e to the negative x over 2 minus, and then sinh was e to the x minus e to the negative x over 2. And we need to take each of those and we need to square it. And we're trying to see that it's equal to 1. Let me leave the 1 off and let's see if we actually get 1. So I'm going to square the numerators first. So we'd have e to the 2x, and then we'd multiply these two things. E to the x times e to the negative x, that's simply equal to 1, and then double it, we get a 2. And then we'd have e to the negative 2x. So that's what we get when we FOIL out that first numerator. Move that parenthesis so it's really clear we're squaring out that. Minus, then we're going to square the second one, so we'd have e to the 2x. Again, when we multiply them, we get just a 2. And then we'd have a plus e to the negative 2x all over 4 and then 4. Let me leave it over two separate fractions first. So we've just squared so far. If we collect our like terms, we'd have e to the negative e to the 2x minus e to the 2x, they cancel. E to the negative 2x and e to the negative 2x, they cancel. So we're left with a 2 minus a negative 2 over a 4. And that's simply going to be equal to 4 over 4, which is equal to 1. So we could prove all of these in the same way. We just replace them with what the sinh or the coth or the cosinh, whatever they're equal to, we'd replace them, we'd simplify, and we'd get 1. I want to move on and talk about the derivatives, however. The derivative of cosh u is equal to the derivative of e to the u minus e plus e to the negative u over 2. So I'm going to actually find this out. So if we want to take the derivative of cosh, we're taking the derivative of this function right here. And so I'm going to apply my, for one, it's just a constant multiple of 1/2. Apply my derivative rule for e to the u, which is just e to the u, times the derivative du dx, if we're assuming there's some sort of inner function there. The derivative of e to the negative u is negative e to the u du dx. And so I'm going to write it back over the, I forgot the negative on the second one, write it back over the 2, and I'm also going to factor off the du dx. And notice what we have here. E to the u minus e to the negative u over 2 is simply the sinh function times du dx. Sinh of, in this case, we're calling it the function on u. So the derivative of cosh is the sinh function. That's similar to our trig functions, but it was actually negative before, right? So this is a positive, very, very similar. but the derivative of the cosh function is equal to the sinh function times the inner derivative, of course. We've done that many times. If we're to take the derivative of the sinh, I'm not going to do the work behind this one. You can do it yourself. I'd recommend practice a few of these, so maybe do the derivative of sinh and cosinh and a few of them. The derivative of the sinh would be equal to the cosh function times the inner function du dx. If we take the derivative of the tangent function, derivative of tangent of u is equal to the sech of u squared du dx. That should look very, very similar to what we remember from before. The derivative of tangent is just secant squared. Here we're dealing with the hyperbolic functions, but it's the exact same. It even keeps the same sign in this case. If we look at the derivative of the coth function, that is equal to the negative cosech squared u du. So it's exactly the same du dx. It's exactly the same as the trig again. The derivative of the sech function is equal to negative sech tanh du dx. So that one's a touch different again because derivative of secant usually is a positive secant tangent. Here we have a negative. And then the derivative of the cosech function is equal to negative cosech cotanh du dx. So this one actually the same as it was with our original trig functions. So some same, some different. Really, they're only off by a sign. They're only ever off by a sign. The derivative of cosh is exactly sinh. We've dropped the negative versus the sech. We've now picked up a negative. So slight differences there, but otherwise very, very similar. We can go forwards and backwards on these. Just like we could with our trig functions, we should be able to integrate along with take the derivative. So let's just do a couple examples with each of these. Let's say we want to take the derivative, find y prime given y equals the natural log of the coth of 3x. All right, so y prime, first thing we see is natural log, so we have to write 1 over interior of it, the coth 3x. Derivative of that coth function, which is the negative cosech squared x, but it's not really x, it's a 3x because that is our original inner function. And multiply that by the derivative of the inner function, which is just 3. So we can multiply that all together, negative 3 cosech squared 3x over the coth of 3x. And so again, pretty straightforward. As long as we know those derivatives, we're just applying the same chain rules we're used to. Really no difference there. And we can apply these forwards and backwards. So let's say we want to find the integral of, let's say we have a 2 sinh of 5x dx. Well, what function gives us a derivative of sinh? That would be the cosh function. And it can't just be the cosh of x. I didn't have an extra x in here. I want it to just be the sinh of 5x, not a sinh x of 5x. Sinh of 5x. Well, we'd have to have the cosh of 5x. Now we had a coefficient of 2, but if we think about what else we need now, it's got to be 2 over 5 because we'd have to apply the chain rule there. So this would be our integral. We need the plus c there because we have to take that antiderivative. And we have to remember it's the most general form of the antiderivative. So we need to know these derivatives, but once we have those, we apply them in much the same way. And the nice thing about the derivatives is they look the exact same as the trig functions. The only difference are some signs. We had let me circle the ones that are different. The cotangent has no negative, it is a plus. The secant, or what's turned into the sech, is now a negative. Those are the two differences. Otherwise, they are the same as our earlier trig functions. Then finally, let's talk about the inverse hyperbolic functions, because anything in math that we can do, we have to be able to undo as well. And so we have inverse hyperbolic functions. If we think about what these are doing in theory, these would be taking our points along the hyperbola and getting us back to that initial hyperbola, or that initial position in terms of the angle. Given some angle, right, the hyperbolic function takes the angle and it gives us the position in terms of the curve. So this would be taking the position on the curve and giving us that initial angle. And so let's start with some identities. The inverse sech function of x is equal to the inverse cosh of 1 over x. Remember, the reciprocal function, sech, is equal to 1 over cosh. But because now we're looking at the outputs, we have to take the ratios of the inputs of these inverse trig functions. That's why we have the x and the 1 over x. If we were to look at the reciprocal function for the cosech function, it is the sinh, but again, because we're now looking at the outputs, we have to take the reciprocal of the inputs. So we'd have cosinh inverse is equal to the sinh inverse of 1 over x. And then same thing with the cotang and the tanh. We'd have the inverse cotang of x is equal to the inverse tanh of 1 over x. So these should align with our knowledge of what we did with the inverse trig functions. We had to think about inputs versus outputs, and reciprocals apply to the output. Once we start with the output, we have to switch the inputs reciprocal. If we think about their derivatives, let's think about the derivative of the inverse sinh function. Let me call it a u so we can apply our chain rule if necessary. Well, that would be equal to 1 over square root of 1 plus u squared du dx. That should look pretty familiar. It is the same as the derivative of the inverse sine. The cosh inverse is equal to 1 over square root of u squared minus 1 du dx. Now there is a restriction on this one that u has to be greater than, excuse me, not 1 but 0. U has to be greater than 0, has to be a positive. The derivative of the inverse tanh of u is equal to 1 over 1 minus u squared du dx. And here the absolute value of u must be less than 1. These are just based on the properties of inverses. Remember, inverses, we said, in order to have an inverse, we have to be 1 to 1. That's what these conditions over here on the right are guaranteeing. Remember, with our hyperbola, we have 2 halves of it, so we could be looking at the positives or the negatives. We need to have a 1-to-1 function, so that's why we're chopping it off, so that we get that 1-to-1 nature. The derivative of the inverse cotang of u is equal to 1 over 1 minus u squared du dx, where our absolute value of u is greater than 1, giving us the other half of that. The derivative of the inverse sech of u is equal to negative 1 over u square root of 1 minus u squared du dx, where our u is between 0 and 1. I should say our u, I'm using u's here, not x's. Our u is between 0 and 1. And then the derivative of the cosech x is equal to negative 1 over absolute value of u times the square root of 1 plus u squared du dx. So we see some similarities again here between the inverse trig functions and our inverse hyperbolic trig functions. The inverse hyperbolic trig functions, I do want you guys to do some examples to be comfortable with these. I'm not going to, on this test, require you to know these definitions, these derivatives rather. I do expect you to be comfortable with the derivatives of the non-inverse, so just the sinh, the cosinh, the tanh, cotang, the derivatives we did before. These ones up here, I expect you to have memorized because they are basically the same as what we did before. You should know what sine and what the sinh and cosinh are in terms of their definition: e to the x minus e to the negative x over 2, and e to the x plus e to the negative x over 2. You should be able to manipulate those identities. Should be comfortable working with any derivative or inverse, even these when you have these sitting in front of you. So you will see these on the homework, on the labs, so do get comfortable working with these derivatives.